In this video, we will discuss the problem sorted and rotated minimum. The problem says that we'll be given an array and we have to find the minimum element in this array where the array is rotated and sorted, and all the elements in this array will be distinct. For example, if you see the first test case, so we have got the array as 5, 6, 1, 2, 3, 4. So the minimum element is 1, so we return 1. Next test case is 3, 1, 2. So the minimum element is 1 here. Next test case is 4, 2 and 3. So the minimum element is 2, we return 2. So the array has been rotated at one point and now the array is sorted and rotated. So we have to return the minimum element. So how can we solve this question? Let's have a look at the approaches here. Now the basic and the brute force way of doing this would be that whatever array has been given to me, let's say if I have been given the array as 5, 6, then after that 1, then after that we have been given 2, 3, 4. Suppose this array has been given to me. What I can simply do is I can basically iterate throughout the array and store the minimum element by traversing whole array. Okay, so this would take how much time? Because if I'll iterate all the elements of the array, then I'm going to take order of n time. So the result finally would be what? The result will be basically 1, because when I'll iterate, I'll find out that the minimum element in this array is basically 1. So I'll update my minimum or my resultant element to 1 here, and this will take order of n time because the time taken will be same as this will take order of n time. The reason being because we are iterating throughout the array, and if you see the space complexity, it will be constant in nature because we are doing what? We are not using any extra space, we are just using a resultant variable here. But can we do it in a much better fashion? Yes, since we have been given sorted rotated array, so we can use the concept of the sorted array, and we can apply the binary search by applying some observations here. So let's see how we can do it more optimally. Basically, we can apply the concept of binary searching because we have been given a sorted rotated array, so we can apply the concept of binary search. Okay, so what we can do is, initially if you will see, so the low is basically initially starting at 0. Okay, high will be starting at the last index, so high will be at 8. Now when I find out the midpoint, mid will come out as what? Mid will be basically equal to 4 here. Okay, that is this particular element here. Now if you see, the element at the mid index is 74, and what is the element at the high? So element present at the high index is basically 28. Now if you observe, the element at the mid index, it is greater than the element at the high index. Okay, you can observe here that at this point in time, the element at the mid index, it is what? It is greater than the element at the high. This indicates what? This indicates that the array from the low till mid is sorted. Okay, the array from low till mid is sorted, and since the the element from the low till mid are sorted in ascending order, and since the mid element is high, greater than the ARR of high, so this indicates that the dip will be found on the right side of mid. Okay, so that is why what I should do is I should basically update my low equal to what? Equal to mid plus 1 here. Why? Because if my mid index that I am at, if it is having value greater than the ARR of high, this means that the dip will lie on the right side. The minimum element will lie on the right side. Okay, so that is why we need to update the low to what? To mid plus 1 here. Now after this, if you will observe, so what will happen now? Now my low will be equal to mid plus 1, so it will be standing at the index 5 now. So now my low will be standing here. If you will observe now, what will happen? So when I take out the midpoint again, what will I get here? When I take out the midpoint again, so 5 plus 3 divided by 2. So this will be how much? This will come out as 6. Now which element is there at the index 6? So if you observe, at the index 6, I have got 14 here. Okay, now is the element at the mid index, is it greater than the element at the high index? No, because the element at the mid index is 14, it is not greater than the element at the high index. So this means that currently the element at the mid index, it is lesser compared to the element at the high index. So this indicates that we can basically conclude that the minimum will lie on either on the mid or on the left side of mid, because if the element at the mid index, if it is lesser than the ARR of high, so this means that the right half is basically sorted. This means that the right portion is basically sorted from the mid, and the minimum will lie either on the mid or on the left side of mid. So that is why what we will do is we'll update the high to mid here. So in the else case, what we need to do is we need to update, basically in the else case you can say that we'll update what? We'll update the high is equal to mid here, because if the element at the mid index, if it is what? If it is lesser than the ARR of high, so this means that the elements on the right side are sorted in this range, and either the midpoint will be the lowest, either the midpoint will be the minimum element, or the elements on the left side of mid. So the range will be, the range for searching should be from low till mid here. So that is why we have updated the high to mid at this point in time. So what will happen because of this? Now the high will be updated to mid, so high will be updated to what? 6 here. Now when I find out the midpoint again, what will I get? When I find out the midpoint, now I'll get what? I'll get basically 5 here. Now at this point, the mid is starting at the index, which is basically 5, and the element here is 89. Now if you observe, what do we conclude here? Now the thing is that the element at the mid index, it is greater than the element at the index high, because element at the mid index is basically equal to 89, and element at the high is basically equal to what? It's 14. So the first if condition is getting satisfied, that the ARR of mid, it is greater than ARR of high. So this means that the dip will lie on the right side of mid. So we'll update the low to what? To mid plus 1. When we do that, then the low is equal to what? It is equal to 6. Okay, because when low will be updated to mid plus 1, so low will become equal to 6 here. Now at this point of time, you can observe that when we have a single element, then that will be the minimum element itself, because if there is a single element in the range, this indicates that that particular element is our minimum element, and basically you can understand that the element at the index 6 is definitely our minimum element for the given array. So what is the terminating condition here? You can understand that whenever the low and the high became same, so that was our minimum element. So the condition that we should keep for termination is that when the low is less than high, till that point of time we'll iterate, because for searching there should be at least two or more element in the range. When you have single element remaining in the range, this means that you have found out the minimum element of the array, of the sorted rotated array basically. Okay, and at the end you can do what? You can return ARR of low here, because that will be the minimum element of the array, because at this low index you can see that it is standing at the index 6, and the element here is 14, which is the smallest element of the rotated sorted array here. Okay, sorted rotated array here. Now let's see the code for this as well. What we'll be doing here is, we'll basically initially update the low to 0, high as mid minus 1. We'll iterate while low is less than high. Now why we are doing this? Because whenever low and the high become same, whenever they become equal, that will indicate that we have only one single element. When only one single element is there in the range, this means that element is the smallest or the minimum element present. When there are more than two elements, when there are more than one element, then we'll keep on searching. So we'll check if the element at the low index, suppose that if the element at the low index, now this is one case that we should also keep in mind, that if the element at the low index is lesser than the element at the high index, so this means that the current subarray that I am at, okay, if the starting element of that range, if it is lesser than the high, this means that the array is completely sorted. So for example, this particular case you can observe, let's say if I had something like 1, 5, 7 and 9, suppose, and my low was standing here, my high was standing here. So if this is very basic case, if my low element at the low index, if it is lesser than the high itself, so if in this range, low to high, if the element at the low index is lesser, then it will be basically the smallest element of that range. Now sometimes what might happen is, you might have been given a different array. Let's say you might be given 10 and 20 here also, but still after some time, if your low is standing here and high is standing here, so you can observe that if the element at this low index, if it is lesser than the element at this high index, then that will be the smallest element possible. Okay, so this is one case that we should keep in mind as well. Now after that, what we will do is, we'll find out the midpoint, and then as I said, if the element at the mid index, if it is greater than the element at the high index, that is what we observed in the basic dry run. So this means that if the element at the mid index, if it is greater than the element at the high index, so the depth or the minimum element will lie on the right side of mid. So update the low to mid plus 1. Otherwise, if the element at the mid index, if it is less than equal to the high, so understand one thing, that if the element at the mid index, if it is less than equal to the high, okay, so this means that the array is somewhat like this. Okay, so if the element at the mid index, if it is less than equal to the high, so this means that the minimum element will lie between the low to the mid. Okay, either the mid can also be the minimum element, or it will lie somewhere on the left side of mid. So the highest point will be mid here. Okay, so we'll update the high to mid here. And at the end, we need to return what? We need to return the element, the minimum element, which will be ARR of low. That is the single element remaining here. So I hope you have understood this. This code will take how much time complexity? This code will take the time complexity, which is same as binary search. That will be order of log n here. And the space complexity for the code will be order of 1. Now let's try and submit this code as well. So let's submit this code now. So you can clearly see that the code is getting accepted. I hope you have understood this. Make sure to comment understood in the chat. Thank you for watching this video.